Everyone, we talk about continuity. So first, let's define what continuity really means, okay? Because we might have an idea of what it means. Practically, say you're drawing a graph or a function, and you can draw the function without picking up your pencil. Then it's continuous. Okay, that's kind of an elementary way that we can describe continuity, but we need a mathematical way to prove it because you can't just say on the AP test, I drew it without picking up my pencil, so it's continuous. You ain't gonna get very far. So we have three things that we look for. Okay, first we look to see that the function is defined at the point. Okay, so we're just defining continuity at a single point at C. Right, then we look at the limit. So we say that the limit as x approaches C exists. Right, and then last but not least, we equate these two. So I say that the limit as x approaches C of f of x actually equals the function at that point. Right, let's break this down a little bit. Our first one is just saying that the function exists at the point. If it didn't, obviously there'd be a hole or something like an asymptote and something bad's happening. Now remember, limits are essentially expectations. So we don't know what's happening at the point, but we can expect or we can kind of predict what's going to happen given the behavior from the left and from the right. Right. So this second one is an expectation. So we have an expectation, it exists, right? And then third, expectation actually equals reality. Right, let's talk about some things you already know. A point discontinuity will look something like this. Okay, that's also called a removable discontinuity. So this is at C. Sometimes it's defined at another point, but whatever. Okay, jump discontinuity, that's typically with a piecewise function. So it looks something like this. Okay, those definitely don't look like anything else. And then an asymptote is an asymptote. So say we have an asymptote and we have some functions doing some stuff. All right, so obviously these are functions you cannot draw without picking up your pencil at some point. These are not continuous, but also they do not follow all three of these rules that we have. All right, let's keep going. Okay, so in these two examples, scroll up a little bit, these two examples we're given a function, and first of all, let's just find where we're discontinuous. So right off the bat, I notice that if I plug in 3, right, I get 0 over 0. That typically means that I can do something to it, and it won't give me 0 over 0. So if I factor the top, I have x minus 3 and x plus 2 over x minus 3. Well, look at that. I can remove the discontinuity, which is why we call it removable. So I know that my function will look like x plus 2, but it also cannot exist at 3. So it's linear, but at some point, I should erase this. At some point, at 3, I have a hole. All right, so that's what my function looks like. For our next example, bad asymptote, I see it right off the bat. Okay, if I plug in 3, I get 1 over 0. Okay, it's not 0 over 0, it's 1 over 0. That's just bad. So I know that at 3, I have an asymptote, and the rest of my function will look like this. And it's the reciprocal function. All right, so we're good there. All right, and last example, we're given a piecewise function and we are trying to force it to be continuous against its will. So we have to find a k value that will make this continuous. Now, I can use the idea of limits. So I know that for a limit to exist, which is one of my conditions of continuity, the limit from the left has to equal the limit from the right. Okay, I know that about limits. And because I have a piecewise function, I'm actually going to use different functions. So from the left, I'm going to use this top function, x plus 3. And from the right, I'm going to use that bottom function, kx plus 6. That's a k. Kx plus 6. Right, and if I go ahead and plug in these 2's, I get a 5 here. I get 2x plus 6. All right, so if I solve for, what am I doing? Sorry. I get 2k plus 6. So if I solve for k, I get that k is negative 1/2. Alright, so if I take this k and I plug it in, my new function is really x plus 3, and then negative 1/2 x plus 6, and then all this other information. Alright, so let's graph this. I know that I have some important points at 3, and then at 5, at 2, 5. Alright, so my first function right here, I pass through 3 and I'm increasing, so it looks something like that, up until right here. That's where it stops. And then my next function, negative 1/2 x plus 6, it starts right here, and then it keeps going. Alright, looks pretty good, looks continuous to me, so we're going to stop there, and I will see you all later.